All right, before we do the recap, I want to mention two things. So number one is, for your ultimate project, it's going to be a team of either 2 or 3 people there, most likely. So I would suggest, if you have seen your fellow students in the class in person, so why not make some friends and then think about who your potential teammates might be. Think about it. Some of your fellow students may not come to class even, in which case there's no way for you to connect to them. I might try to set up something on e-class maybe when we get closer to the project day. So for those of you who are looking for like a teammate, maybe you can connect over e-class virtually, but I would say if you know somebody in person, why not, right? You can interview them, they can interview you as well, right? Have some mutual agreement. So think about it. I'm not going to assign you some group, it better be voluntary, right? So think about it. It's definitely have time to think about this kind of stuff, because it's going to be somebody you're going to work closely with for 6 weeks on the project, which is going to be a very big learning component for this course. So you guys can plan. If you need any assistance in finding teammates, you can feel free to let me know. I can even initiate this maybe a little bit earlier. That's not a problem for me. Okay, just let me know. Right, the second thing I want to mention is, which can also be useful maybe for you to come up with some side project yourself. Right, I'll show to you. There was an e-class announcement I made earlier. So if you go to the e-class, so there is one section there called past projects. So this is the 3rd time I'm teaching this course. So in the previous 2 iterations, we actually got two very different projects there. So I got the project instructions, exactly how it is supposed to be delivered, exactly how it is supposed to be understood, and also some high level, like a visualization. And this is like a project number 1. That's one kind of compiler you can build. And also for compiler number 2, compiler number 2 is actually here. That one was more recent. That one was done maybe back in fall. I may just have to rename that. Okay, one of them is done in fall 22. The other one is done in winter 20, right before the lockdown, actually, for pandemic. So you can look at these 2 project description there, look at the diagram, and maybe hopefully that can give you some inspiration. So we'll see how the time goes today, because I really want to go into the lexical analysis, at least do some introduction. So we can start with it. But if we got any time, maybe a few minutes, I don't mind actually going over with you very quickly at a high level what these 2 projects are about. They're actually very different in their nature, but they can all be done using a compiler. So that really gives you some idea. Compiler really gives you so many opportunities to build something useful. So that can be also something you guys can plan throughout the semester. All right. Any question about the course in general? All right, good. Let's now do a very quick recap, and then we'll continue with the last example compiler, which I want to give you a little bit more concrete idea about what an object relational bridge can look like. But before that, let's now look at what we said last time, quickly. So last time we actually still focused on the high level view about what a compiler is, and we introduced this intermediate level here, optimizer. So we got front end, we got optimizer in the middle, and we got back end. Of course, in general, you may have as many optimizer as you see necessary. So optimizer here, optimization is a very general term. As long as you're improving something into something else, then that'll be like an optimizer. It can be just to improving the number of classes you want to have in the input, or can be optimizing the number of variables you're using, or to organize the imports. You want to get rid of all the unused import statement in the Java file, right? Things like that. It can be very general. So I'm not going to repeat the details, but you guys can refer to the 3 different requirements that we kind of need to impose when you got 3 components in your compiler, right? Think about the components over here. As I said, in your project report, ultimately, you will need to somehow justify why your compiler is actually correct. We don't really require any proof, like a formal proof, but at least some reasonable justification will be expected. Okay, that's something we can talk a little bit more about later. And this is the very conventional compiler, which will turn C-like program into low-level instructions, where we got a very long pipeline of semantic analysis, right? That's just another example. But this is not how we're going to structure your projects. We want you to do something a little bit different, rather than just from some programming language into assembly code, right? That's something you definitely can do as well, but we want you to do something more interesting. So TS and I, we're still trying to come up with new idea for you guys, for the project, but it will be released in time. But at the same time, you can also look at the previous 2 projects just to get more idea. All right, we talk about the different levels. So lexical analysis and also syntactical analysis. So these 2 are the routine practices that can normally be automated. But in the lecture, we also dive into their theoretical foundation. Because the theoretical foundation is so well built, so that's why they can be automated. But we're going to learn about how they can be understood from a theoretical point of view. Quick recap. So when you are given some input program, you can think about there will be multiple passes of the same program, depending on which stage you are. If you are in the lexical analysis stage, you're going to pass through your input program character by character. What you're really aiming for is, whenever you see some character sequence over here, you're trying to see whether or not the character sequence is going to be recognized as a valid pattern. And the pattern can be specified using what you learned in 2001. It could be a regular expression, which is most likely the case for entler 4 you're going to learn. Or it could be DFA, or it can be NFA, etc. That's also something we're going to start talking about from the later half of today. So the first level is we're going to do lexical analysis. We want to make sure every token over here. When I say token, think about your entire program can be separated by different delimiters. So it could be space, it could be some opening brackets, or it could be some closing brackets. You want to think about all the things between are supposed to be treated as token. We want to make sure all the tokens are spelled properly. They will be recognized by some pattern. For example, if I spell this one just with a single S, CLAS, it's not a valid token for sure. Or let's say if you go to your email account, if you want to create a new email account, you want to create a new username. Typically, the rule will be you cannot start with your username with some special symbol. Can I say #Jackie, for example, as a username? I cannot, because apparently this one here is going to violate the pattern, so it's not a valid token. It fails the lexical analysis, first of all. Great, different example here. Let's say your lexical analysis actually passed. In that way, the output will be a sequence of spelled correctly tokens, right? So each token over here is somehow going to be used to build a valid parse tree, or at least we attempt to really build a parse tree. If we are able to build a parse tree, that means the grammar is actually correct. So we pass the second stage. Exactly how we can go from this linear sequence of tokens over here into a parse tree, that's also something we're going to dive into. As I mentioned last time, there will be something called a top-down parsing algorithm, and also the bottom-up parsing algorithm that we have to learn. We're going to dive into each one of them deeply. And I would choose one of them as your third assignment for you to try it out, just to implement it. It's not too difficult, right? So the pseudocode is somehow presented in the lecture. I just want you to try to program it in Java just to get more details, right? So you can get some exposure to how things work behind the scene. Right, we'll definitely dive into detail about how you can transform from sequence of tokens into parse tree. We'll talk about it later. Okay, so if we can build a parse tree, that means now we get some abstract syntax tree that can be subject to a series of semantic analysis, as many as you like, before you can output the final program. Right, that's really the stages we're talking about. Right, we'll talk about analogy. Words, sentences, and meaning, they simply correspond to lexical, syntactical, and also semantic analysis. Right, that's something we said last time. You can review the ideas. And semantic, yep, and then grammar. So this is one example of the context-free grammar, and we're going to look into that also. And if you guys recall, back in 2001, specifying a grammar like this doesn't really guarantee it's going to be unambiguous, right? I'm pretty sure you learned about the notion about a grammar being ambiguous. If you actually got ambiguous grammar, then most likely your compiler cannot function well. That means given 2 input strings, you might actually generate different parse tree, non-deterministically, in which case you simply don't know which meaning you should really extract from your input. That's also something we're going to dive into, just to review from 2001. All right. And then we'll talk about one example compiler where we simply give it an input program. We just want to somehow improve its runtime performance. So what we did last time was to identify this particular expression here doesn't need to be computed every time because it should just stay invariant, stay the same. So that's why in the optimized program, we simply move this expression over here to outside, only compute it once. So that's one optimization pattern. overall, let's now summarize. Okay, overall, right here. So this is one single diagram here. You also see on your slides. Let's now review this, and then we're done with the recap. Okay. From the user's point of view, external user, they are only seeing this. Okay. So let me just recap again. So this part here is really from the external user's point of view. This part here. So you go from the input program, and somehow it is optimized automatically into some output program that's more efficient. So this is from the external user's point of view. They don't understand anything about M2 They don't understand anything about parsing, pretty printing. All they know is, I write this program here, somehow it will be optimized automatically. How exactly that can be done from your point of view, you are the implementer of the compiler, it's going to work like, you're first of all going to pass the input program into some parse tree, right? So this is the parse tree for the not so efficient program. And then for you, you're actually going to make sure it passes, once you get a tree here, assuming that it passes the syntactic analysis, we are going to implement some transformation function in Java, in your case. Once you have done that, you're actually going to transform that into basically a different tree. And this tree over here basically represents just another equivalent program. The behavior should be the same at the runtime. It's just more efficient. Okay, that's very important. Let me write it down. So you think about this is program number 1. This is program number 2. Okay, so we said that number 1, program number 1 behaves the same as program number 2. Program number 2, semantically the same. They really mean the same thing. Number 2, program number 2 is going to execute faster, or it's going to exhaust less computing resources. So it's going to be program number 2 is more efficient. Then program number 1. Okay, one more thing to say. Sometimes we also say this is a semantics preserving transformation, because we don't really alter the meaning. Semantics preserving. Preserving transformation. Okay, semantics preserving transformation. As far as the runtime behavior is concerned, the unoptimized program and the optimized program behave the same. Okay. And finally, once you got this final tree that you have, you're comfortable, you're happy with it. So now it can simply traverse the tree and output the program. That's why I said pretty printing. It's the reverse operation as parsing. Okay. Okay, I mentioned a term about commuting diagram. So this is, okay, let me just say this will be the final stage, and we just pretty print it, right? From the external user point of view, just from one input to the output. But for you, you should really know that you should really parse transformation for as many stages as you like, and then pretty print. Okay? Yes? Yeah. In this case, the input and output just happen to be the same, but they don't need to be. Of course, in the more general sense, you can translate, for example, from Java into Python, in which case input and output are different.
So it's still the same?
Still the same process. So the way things commute will just be the same. Commuting diagram is very useful here. Yeah. All right. So that's about the recap from last time. And do you guys have any questions? All right, the final example I would like to talk about, right? Let's go over a little bit of slides. But guys, I want to give you a little bit idea over here. So this compiler, it's actually a compiler, of course. The compiler itself is pretty complicated. So I'll try to present to you just about the high level detail with some example. So don't worry too much if you don't get exactly the details I'm trying to present to you, right? Just get a high level idea. I'll keep reminding you, okay? Let's now go over some slides, and then I'll show you the example. Okay. So what we want to do is we want to implement a compiler, a transformer, to go from, I said, object-based rather than object-oriented. The reason I said object-based is I only got classes attributes and also methods. I don't really have things like inheritance, polymorphism. I don't have that. So I'm restricting my input to be just object-based, which is pretty common. So when you design your projects later, I will require you to kind of design a programming language on your own, in which case you got to think about what kind of restriction do you apply to your design so that you don't really have to implement a very advanced feature that's not even possible, right? So always remember, you can always restrict the input grammar so that you can avoid certain infeasible feature to be compiled. Okay, so domain-specific language, in this case, object-based. And we want to generate it into output that's SQL database queries. Okay, I'll talk about the different parts in a moment. Okay, so now, first of all, why are we doing this? Okay, input is actually object-based. Output is actually relational. So think about why we're doing this. So input is supposed to be, let's say from the external user's point of view, the input that's object-based is going to be written or used by some developer. So a developer might just find the object-based language to be higher level, easier to understand. It's easier to understand in terms of classes and objects and attributes as opposed to just tables, keys, and queries. These are a little bit lower level. That's one argument for object relational compiler. So we can separation of concern. We say that. So there's a table here. I'll just summarize it together with you over here quickly about why we're doing this. So there are basically two criteria we are actually considering. Okay? So first of all, we say why object relational breach. Why do we bother with that? We want to think about two different semantic domains, which is objects and also relational. And then we want to think about different criteria for us to judge which one should be the input and which one should be the output. One criteria could be, so let's say criteria. So let's say one is about how you can specify or how you can model versus how you can do storage of your data and also how you can retrieve. So these two aspects are very different concerns. One is only about how you can express the ideas for your business solution. For that one, you may want it to be as high level as possible. So the concern over here is about level of abstraction. Higher level of abstraction the better. Well, think about if I ask you to build a large system, would you rather build a large system written using Java or writing that using assembly? Of course, Java, because it's a higher level of abstraction, right? So specify and modeling, that's one concern. And here is about storage and retrieve. How can we store a large number of objects? How we can store a large amount of data? And we want to retrieve them also efficiently. And also sometimes you may have to make some concurrent queries to your database or your storage, in which case you want to make sure the transactions can be done properly when you got multiple concurrent transactions happening together. All right, so here the concern could be definitely efficiency. And also concurrency can also be some concern, right? So they are very different consideration over here. Okay, based on these, so you can see we got either this or this as semantic domain. We got this or this as the concerns. Let's now try to work out what might be the way to go. Okay, so let me just draw the table here. And like that. Okay, let's talk about object first. For object over here, it's definitely good for specifying and modeling. Because if you think about think in terms of classes, attributes, methods, dot notation, context object is definitely very high level. As for relational, it's not good because you're thinking in terms of tables, keys, queries. Think about how you write nested queries. I'll show you some example. Okay, it's actually pretty complicated. This one here, for example, you got nested queries. And you will see one concrete example in just one moment. As opposed to, if you got objects, normally what you do is the dot notation. What I meant was, if you got some object O.N1.M2, etc. You just write that. You don't need to write anything that's nested. Okay. What about storage and retrieve? Well, relational database like a SQL, they are known to be very reliable in terms of a concurrency or transactional control. So definitely, this will be a plus. On the other hand, for objects, the best you can do is to serialize your objects. You may have heard that word before, but I wouldn't dive into much detail. But the idea is, whatever object you have, you somehow have to recursively figure out the contents of the objects and write them out into files. It's not very efficient, okay, compared with the databases. No. Okay, I'm just trying to show you the rationale about thinking about, should we go for object relational breach, or should we go relational object breach? Right? That's really what we're thinking. So it turns out we want this guy here, specify model, to be the front end. Well, to be the input. And we want this guy over here, about storage retrieve, to be the output. When we, as a user, when we want to construct the input, we want to focus on high-level stuff. So it's easier for us to build something big. On the other hand, if we can have some automatic transformation to go from input here into output over here for mass storage and retrieval, then that's great, right? So it turns out we're going to choose for the best from two worlds. We want to choose for this one here and also this one here. Okay, that's just the rationale. So object over here is going to be the input, and the relational over here is going to be the output. So that's really the idea about why we need object and relational breach. And let's see how we can do it, right? It's more like a design phase to make sure we know where to go. All right, and then the challenge is object and relational, they are two very different semantic domains, as you will see. So we're going to make sure any automated transformation we implement has to be somehow well-defined and also correct. Okay? I'll just give you some example today so you can see some idea. And there's one paper I kind of included at the end. Optional, if you're interested diving into more details, feel free. All right, so let's talk about input here. I kind of described, okay, so there are two parts for the input. One is about the data model like a classes. And the other one is about behavior model, which is about like a methods, right? I'll talk more about the classes to get some idea. So data model is going to be classes and also association. I'll give you one example here. Okay, let's talk about this example. Okay, data model. So you can think about this data model here, kind of represent the relationship among different classes. For example, you can see this one here is one class. Hotel. This is a single class. And then you will see that there is some binary kind of relationship between hotel and traveler. And also between account and traveler, we got this one here. It's called association. I'll just explain one of them, but I can look at others just in a similar fashion. Okay, let's say this. If I look at this particular association, okay, this one here, this one right here. The way to understand it is, usually association will be bidirectional. This is how we can interpret that. We are saying that each account object has exactly one owner of type traveler. Symmetrically, each traveler has 0 or 1 optional account of type account. I'll write it down. Okay, it's a by association. By association. Okay, Direction number one, from left to right. So if you go from here to here, each account has one traveler as its owner. One traveler as its owner. Okay, that's number one. And symmetrically, we say that each traveler has 0 or 1 account as its travel account. Okay. Each traveler has 0 or 1, right? 0 or 1 right here. Account as its travel account. Right? So you get the same idea for all the association there. So we talk about a particular data model, the system for hotel management. You can see we got 1, 2, 3, 4, 5, 6, 7, 8 classes, and also about close to 10 different association, right? That's kind of like a more, not exactly like a very complicated model, but at least it's not trivial. Okay. So this diagram here kind of specify the data that we want to eventually store. But at the, from the specification point of view, having this notation here is very valuable, right? It's easy to understand. Okay, and let's now take a look at some example here. And then we'll show you something. Okay, just one moment. So let's say here. So there is one particular, let's say, oh, the one we just talked about is right here, right? You can see that's the association. Programmatically, how do we declare that? For example, just one example here. You can see account over here. Account has one traveler as the owner. Programmatically, class account has exactly one traveler as its owner. All right, just try to show you the correspondence. And by the way, this account over here, just part of the syntax. This one tells you that it's a by association. This particular association has the symmetric link back to the account. And for that, I wouldn't dive any deeper, right? That's just specific to this particular compiler. That's the input language. If you want to implement this compiler, you have to somehow define the grammar, context-free grammar, which will take something like this, and then somehow build a parse tree and then process it. Right? That's as far as I want to go for that. Okay? And I'll give you example very soon, like a concrete example, like how table would look like. All right, so we got like a one association, we got just another association, but somehow we just say it's a collection because we got star over here. Star means 0 or more, right? It's like a collection, okay, and etc. And the method here is just, again, it's a more like a domain-specific language. So the syntax might seem a little bit peculiar to you because it's domain-specific. You haven't seen that before, right? So you can think about number one. This is the syntax of a domain-specific language. So you haven't seen that before. But you can define that using context-free grammar. You can define using some context-free grammar. Okay? What I want to show to you is something like this. For example, you will see something like this. So this one here is using the dot notation. Okay? That's something you're kind of familiar from Java, right? If I have a dot notation here, if the T here is traveler, for example. So T here is a traveler. And I somehow want to get access to the list of registration for this particular traveler. So what should I do in OO? I simply traveler dot registration list, assuming that it's an attributes in the class, right? That's pretty familiar. And for other things, you don't need to worry. Just different keywords and also different notation. We don't need to be bothered too much. But if you're interested, really diving into the details for this compiler, you can feel free to see the paper, which are included in the slides. Optional. Okay. So far we have seen two parts for the compiler. We have seen the data model, which is about a bunch of classes, and also the behavior model, which will be just about some methods, and specifically is going to use a dot notation. Here's the thing, the most challenging thing, which I'll show to you, also one example here. You want to think about if somehow I want to turn this hotel management system from classes, attributes, methods into a SQL database. How exactly am I going to work out the dot notation? There is no dot notation in SQL queries. No. How can I do that exactly? Right? The short answer is we somehow want to turn this dot notation here into nested select queries. I'll show you some example. I just want you to see how complex this can be. But even though it's complicated, the user of the DSL, they don't need to be bothered because they know the compiler implementer is going to automate it for them, right? All right, let's take a look at one more example, and then we're done with this compiler. Okay, I just want to dive a little bit more into detail. Two more. Let's look at the easier part, which is table. Okay, let's say, for example, here. Again, let's look at the by association we have walked through. Let's say we got account and also traveler. Let's adjust this one here. So we got account, traveler, and also we got account and owner, right? So here's the rule. Let's say you are a compiler, once you got the abstract syntax tree from the input program, which will be classes, attributes, right? It's somehow going to turn each association into its corresponding association table. That's something you will have to automate, okay? So this one here, you can think about this is going to be turned into, okay, I'll say star. Each by association is transformed into a table, SQL table. And the table itself, so here we got OID. Oh, by the way, when we say OID, right here, OID, 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 OID. It's just like an object ID to simulate how things work in OO. Remember the IR1, IR2, etc.? In order to somehow simulate OO program, we have to simulate what object IDs can be represented, right? Just object ID. Okay, these are just object IDs. Okay. And then you will see we got one table called account. So account corresponds to the account class. Traveler corresponds to the traveler class. Hotel corresponds to the hotel class. And then we got this particular separate table that corresponds to this association. We got this separate table that corresponds to this association. Right? We got so many tables. We got 1, 2, 3 classes in the input, but we got 1, 2, 3, 4, 5 tables in the output. But it's okay. That's what your compiler will do. End user should not be bothered, right? All they want to make sure is whatever DSL, like a Java-like language they write as input, you'll be turned into a SQL database. That's all they care, okay? The final thing is, for methods like this, in the input program, somehow it will be turned into so-called store procedure in SQL, right? It's like also like a sequential composition, like a procedure. But in the SQL database for store procedure, it's not like a Java. You have to somehow use queries executed one by one. So there will be quite a bit of a mismatch we have to handle. One more page, and then we're done with this example, okay? I want to show you specifically the biggest challenge. The major challenge is how we can turn the dot notation in object-based semantic domain to select queries in the relational domain. Relational semantic domain. That's the biggest challenge. And I'll give you just some idea. right here. All right, let's now take a look. Okay. So let's say we already got our runtime structure built up already. Let's say. What we have is, in a table, let's say we got a single account object, and that particular object has ID just 1. And that account has balance 100, right? And also we got 2 traveler objects, OID 2, OID 3, right? We got Alan and Mark, the 2 travelers. And also in the hotel, we only got 1 hotel, let's call it Glad. Right? Also different ID, right? The ID just simply unique. And then we actually got this association here. So here, association, we're saying that for account owner traveler account, this one here, we got owner being Mark. We got the account being this account. Right? We just have some correspondence. Okay? So 3 here correspond to the 3 here, just Mark. And also the 1 here, the account, correspond to just this single account, right? Just how we link the objects together. Okay? Now here's a question. Let's say in the input program, we have this. Okay? We have this object path. Let's say this over here, we are writing this in the context of account class. Let me write it down separately. If I say this dot owner dot rec list. Right, you guys remember the this keyword, right, in Java? I don't need to explain. Let's say we are not in the context of account class. So we know that this over here is of type account. Can we say dot owner? It is actually going to give us traveler, right, by following owner. And then we are going to go for one more level, rec list, right here, rec list. That one there is just going to give me another one here. So rec list is a star, means 0 or more. It's like a set. So this will be a set of hotels. You can see that's pretty easy to see from the input semantic domain because it's OO. Easy to see, right? We just follow the dot and work out exactly the type. That's something you guys are very familiar with. But how do we translate this into SQL database? That's a problem. Somehow we got to look up the table multiple times, and the way we look it up, we got to specify that as nested select query. So when you actually if you want to dive a little bit more into the detail after the class, you somehow want to convince yourself this expression here in the input correspond to this expression in the output. And I'll just point out to you the essence, and then we're done. Okay, these are semantically equivalent. Semantically equivalent. Okay, let's see this. Somehow, when you try to do this nested select query, you can see why it is nested. You can see select right here. I got another select. Somehow the 2 select correspond to the 2 dot, somehow. All right? However, when I go from left to right, this dot owner dot rec list, they start with rec list. And then they go for also the owner. They go the opposite way. Okay, that's another thing to see. So what we're going to do is, for this part, this dot owner, this one here actually correspond to right here. This part here. This part here correspond to this dot owner. How do we understand that? Okay, a little bit about select query very quickly. So we say we want to select from the table here. And then we're going to find out the owner of the column where the owner is corresponding to this. And this is the account that we're talking about, which is 1. Okay, I'm going a little bit fast, but anyway, so the idea will be somehow you're going to run this select query over here and find out what the corresponding owner is. In this case, it will be 3, turns out. Okay. After that, you just got to do another one. You can also take a look. And this final one over here is just going to be the purple one. So this one here is like a dot rec list. And that one simply corresponds to going to this particular table over here and figure out exactly which row you should really retrieve, right? As I said, just get a high-level idea about the complication that might be involved if you want to implement a specific compiler. The very much detail about how to really implement this, it's another story, okay? I just want to give you some concrete details, but you don't need to understand 100%, okay? Just an example, okay? Question. One more takeaway, if you ever want to do such object relational bridge, I can tell you the most challenge you're going to face will be how to transform methods. Transforming class attribute structure into table, they are very straightforward. This not going to be tricky. It's mainly the methods that's going to be tricky. Okay. All right, if you have no further question, I would suggest we take a very short break by taking attendance. And then after the break, why don't we do some introduction to the lexical analysis, see how the time goes. If you do have some time left, I can talk about the 2 past project briefly. Okay? Why don't you get your iClicker ready, please. All right, so now we're done with the intro about the compiler. And then I think everything has been said before the break. You guys can take a look. If you're more interested in learning more about the example compiler number 2, especially about how you can transform the path expression, like a dot notation, I did include some references over there for you. You can take a look, right? So there's a paper over there if you're interested. It's not going to be covered in the exam, so don't worry, right? Just for those of you who are interested, I'll leave that exploration to you. All right, so we're done with this, and we're going to start with a new lecture, and the slides are already on the lecture site. Okay, so we're going to do the lexical analysis. That will be the first stage. We're going to check character by character and see if the character sequence is going to match some certain pattern. And we're going to basically review what you learned back in 2001. Right? Hopefully, we can give you some new insight. Right? For those, for example, that can be done very quickly. I'll also skim through. Okay, I can also assign to you as exercises. Okay. Right, let's now don't forget the big picture, right? So what we are talking about is, remember we got different stages for the compiler, right? So we got lexical analysis, we got syntactic, we got semantic. So in the coming 2 or 3 weeks, hopefully only 2, we are only going to talk about lexical. So once we're done with it, we're going to talk about syntactic analysis. That one there is going to be big, because we got to dive into grammar, ambiguity of grammar, and also parsing algorithm. That one's going to be big. And then we're going to spend a little bit of time. We're going to interleave the syntactic analysis with maybe some design pattern, just to show to you how you can implement some big project using some design pattern, namely composite and also visitor. Well, I'll just mention the name here, but we'll definitely get there. Okay, it's going to be composite, also visitor. Yeah, since the 3311 software design course is not a prerequisite to this course, so if you haven't really learned about design pattern, that's okay. It's not a prerequisite. So the only thing I might require you to at least know coming to the exam will be polymorphism and dynamic binding, which you learned in 2030. So as I said, if you want to get prepared for this lecture over here, most likely it's going to happen after the reading week. So maybe review a little bit about what inheritance, polymorphism, and also dynamic binding work in Java. That's going to be very beneficial for that lecture. Okay, for that part, I'm going to leave to you. All right, so we're going to talk about lexical analysis. Basically, let's summarize what it is supposed to do. You're going to scan through the input character by character. If all the tokens can be recognized as valid patterns. In that way, we pass. And we can move on to the syntactic analysis. When we say pass, that means a sequence of tokens will be output. If there's at least one token that's identified as invalid pattern, in that case, we're going to report some error. If at least one token not recognized as a valid pattern. And let me mention that very briefly. For example, let's say if you somehow use a DFA to recognize the pattern. Let's say after you process the token, which is a sequence of character, and the ending states for that DFA is not accept states. In that case, it should be rejected, right? I'm pretty sure that's something you learned back in 2001, but we're going to review it a little bit later. I just want to mention that. In that way, you're going to fail. When I fail, you got to report error. Report lexical error. So you either go for a sequence of tokens that can be passed to the syntactic stage or syntactic analysis stage, or it might report lexical error. Either way. So there are only two possible outcomes. It's not possible, for example, your lexical analysis doesn't terminate. Not possible, right? Because the way you're going to use ANTLER 4 is going to generate the lexer for you. So it's guaranteed to terminate, right? All right, just keep that high-level description in mind. And then we're going to dive into different theoretical concepts. But before that, let's look at the roadmap of how we're going to review this lexical analysis here. So this is a diagram you also see on your slides. Let me just go to see if I miss anything here. Okay, lexical analysis, upon termination, etc., right? Yeah, so that's exactly what I just mentioned, okay? And this diagram here kind of summarizes how we're going to proceed with the lecture. Let's go over that, okay, to see. Okay, so what we're going to start with will be regular expression, which is right here. Regular expression. So that'll be what we're going to do first. Regular expression. It's more like a textual form to specify the pattern. And then in order for us to kind of understand about a pattern, we're going to just introduce certain concepts, which we'll cover hopefully today at least. So there are several levels of concepts we're going to go over. Okay? So the first level will be something called alphabet. And the next level will be string. And the next level will be language. And the final stage will be about problem. So these are the different levels that we're going to go over today. Alphabet, string, language, and also the problem. Right? We're going to go over them. Of course, they're all applicable to the different pattern language that we're going to go over. Regular expression is the first one we're going to go over. The second one is going to be DFA. Okay, so the second one there is going to be DFA, deterministic finite automata, right? We'll see the precise definition later. Okay, number two. And also we're going to talk about the next one will be number three, NFA. Number three. And then once we talk about NFA and also DFA, we're going to learn about how we can convert from NFA into DFA. Okay. This is something called subset construction technique, which is kind of interesting for us to review. Okay. So this will be number four, which will go from NFA into DFA. Okay. And I forgot the exact order. Maybe either we do this one first, or we'll do another one here about regular expression, right? This one here. And also there's another one here. How can we go from regular expression into NFA? That will be another one. This one here, go from regular expression into NFA. So maybe that's number 5. Okay. 1, 2, 3, 4, 5. And then the final one we're going to talk about, which is a very important stage for the scanner. Ultimately, we're going to start with regular expression. This will be the input language for Antelope 4. This will be the input language of Antelope 4 to generate a scanner or lexer. Right? Sometimes people say scanner or they say lexer. Okay, either way. That's an input language you got to write, regular expression, which is pretty straightforward. I think once you kind of go through the tutorial video I'm going to ask you to study, you will see the most common one. You can just extend that a little bit for your purpose. And then, so we're going to go from regular expression here. First of all, go from regular expression into NFA, and then go from NFA into DFA. And then the DFA over here may contain more than necessary number of states. Meaning that in order for the lexer to be as efficient as possible, we want to minimize the number of states in the DFA. That's something we also want to learn about doing it theoretically. So that is called DFA minimization. So we are basically transforming from one DFA into another. This one here, right? Oh, sorry. This one here into here. It's called DFA minimization. Minimizing the number of states. The fewer states you have for the DFA, the less memory it's going to require. Okay. Imagine that if you are trying to deploy your compiler into an embedded system, then in memory will be very important concern. Okay? So this one here is to minimize the number of states in the DFA. And the DFA over here is the output language. Sorry, I shouldn't go that far. Okay, that's good enough. Okay. Somehow we need to make sure we specify regular expression and it will be turned into DFA, but it also has to be minimized. So we're going to learn about how we can do it manually to minimize the DFA, but you can assume that Antelope 4 is going to do the minimization automatically. Okay? You don't need to implement it yourself. But it's really interesting to see how that can be done. Okay, we'll get there. All right, so that's a roadmap. And then let's now go over some definitions, okay, a bit. Okay, we've got about 20 minutes. Let's see how far we can go. We need some concept like a set comprehension, predicate logic a little bit. So we just review them as we go. I'll just give you just the necessary background. Okay. All right, first of all, let's start with alphabets. Let's go over some definition. A single alphabet is a finite, non-empty set of symbols. So it cannot be empty, first of all. It's got to be non-empty. Let's see some example right away. So over here, we use the sigma symbol to represent the alphabet. But sometimes you may have to add some subscript to explain what kind of alphabet this is. It might be a binary alphabet, 0 and 1. It might be an alphabet corresponding to the keyboard, like ASCII key, right? Could be different alphabet. Let's see some example here. And how do we specify the alphabet? Because it's a set. So we can either use set numeration, just listing explicitly all the set members in the alphabet, or we got to use something called set comprehension. So I'm going to give you example for both. This one will be set numeration. So you can see here, okay, let me just write it down here. Let's see some example here. Alphabet. So alphabet non-empty set of characters. Alphabets. So you can say sigma over here. I can say binary. Then I'm going to exhaustively list all the members, 0 and 1. Okay, 2 symbols there. And then another alphabet, I can say, let's say English alphabet, which will be, let's say, from A, B, all the way to Z, lowercase, and also A, B, all the way to Z. And of course, I can actually calculate what's the what's the cardinality, like a size of the alphabet, right? For example, here, by the way, guys, what should this be? 52, right? 26 for each, right? I got 2 cases. Very good. And of course, the cardinality for a binary over here, just 2. Why cardinality? Okay. So this notation here is about set numeration. It simply explicitly numerates out the members in the set. So that's called set numeration. This one here. Sorry. This one here is called set numeration. Another one is called set comprehension, in which case you don't really have to explicitly write out the members. You somehow specify some Boolean condition. And anything that satisfies the Boolean condition is going to be included in the set. That's a little bit like a more general way of specifying an alphabet. Let's see some example. Okay. Numeration here, that simply list all the members out. Yeah, numerate simply means listing, right? You can think about member number 1, member number 2, right, etc. Okay. And then we got this one, and then we got binary. Okay, how about this one here? Let's start with this one here. This is a set comprehension notation. Okay, that's now, I'll write it down first, and I'll give you the general syntax. I simply call that decimal. Okay, decimal number, decimal digits. So here I say sigma decimal. It's going to be all the digits D. Think about D as like a dummy variable, right? And then vertical bar, 0 less than or equal to D, and D less than or equal to 9. Maybe just by even looking at this, you can kind of see what it really means, right? So we are saying that we're going, so this set over here is going to contain all such D, as long as D is in between 0 and 9 inclusively. Okay? Set comprehension. Yes, that's correct. So this one here is called set comprehension. Comprehension. And we're going to see many examples about set comprehension. As we try to define even DFA ideas formally, we'll also use set comprehension idea, right? So this is something you cannot get around. You have to understand it. But we're going to build it properly. Okay? So for this one specifically, let me write down what it means, and then we're going to look at the general syntax. Set of all such D that is in between 0 and 9 inclusively, right? Of course, if I change this one to be strictly less than, right? In that way, of course, I'm reducing one member from the set. I'm excluding 9 basically, right? And let's now talk about the set comprehension expression more generally. Okay. So set comprehension, I'll put it here. So set comprehension in general. This can be any expression you like. It does not need to be a single variable. Any expression. And then such that vertical bar. And then this part over here is going to be a Boolean condition specified in terms of what's involved in E. Okay? So this is going to be a Boolean condition or predicate. Or predicates involving E. That's a general form. Okay? So the set is going to be all such E such that this predicate here is going to be true. The resulting set contains all such E where let's say this part over here is some predicate, let's say, right? Let me just say predicate P, okay? Predicate P holds. That's a general definition. Okay? We're going to see more example. Let's take a look. Sometimes if you're somehow, this one is not going to be applicable to us for too often. Sometimes you may just describe exactly what the alphabet is like without using set comprehension or set numeration. You might say, okay, I got an alphabet set. It's going to be all the keys you can type on the keyboard. Okay? In that way, you may not want to bother to actually numerate them out, right, using set numeration. So just describe it. Okay. All right, so that's about alphabets. Okay. Guys, any question about alphabets? Good. That should be rather straightforward. But as for the set comprehension, don't worry, we're going to see many examples coming. So we'll just see more and more. Alphabet could be, for example, if you want to try, you want to get some idea, right? What do you mean? Do you want it or you don't want it? You want it, okay? Yeah, just be sure, right? So for example, if you really want to, I don't think you can actually easily do that using set comprehension because it's more like an individual key, right? Something like this. It could be something like, for example, you got all the A, B, C, D, E, right? So A, B, all the way to Z. And also you got 1, 2, 3, 4. 1, 2, 3, all the way. Actually got stuff from all the way to 9. Of course, you can say 0 as well. And then you got some special symbol. Maybe you got exclamation mark. You got @ you got hash, you got $, etc. If you want to numerate them out, just look at the keyboard, right? Put them out, right? Keyboard alphabet. Okay, let's do a little bit more. All right, let's now look at strings. Okay. String is the next level. Given that we got some alphabets, a string or a word, but typically we say a string. Okay? A string or a word is a finite sequence. It's not infinite. It's got to be finite. Excuse me. It's a finite sequence of symbols chosen from some alphabets. Let's see exactly what it means. Okay? So let's say here, for example, the word Oxford is actually a string over the alphabet set English. Okay? For example, I can give you, let's just go over a little bit, and then I will see some formal definition. And also we say 01010 is a string over this alphabet over here as well. Okay? Because you can see that so for example 0 1 0 1 0 is a string over the alphabet of binary. Because you can see 0 over here is a member of the binary alphabet. And also the 1 over here is a member of the same alphabet, and etc. If every character there in the sequence is actually a member of the alphabet you're talking about, then of course it's a string over the alphabet, right? So basically every character over here is a member of that, right? That's how you can understand it a little bit more informally. Okay, and then, yeah, this one here, you can see this string over here is not. How come? What's wrong?
The dot is not part of that.
Yeah, exactly right, right? Easy to see. Yeah, you can see the dot over here. The dot here is simply not a member of this binary alphabet, right? All right, so just one example here. Okay, question for you. So here, I'll write it down. And then I'll switch. You can think about why you think, why you would think that might be incorrect or correct. 0 1 0 1 0. One moment. There we go. All right, the expression is just saw on the slides is this. Does this membership make sense? No? Yes?
Because 0 1 0 1 0 is not a member of this set in particular.
Yeah, exactly. So somehow you think about if you use set membership, right? So what kind of membership, what kind of a set you're talking about? This set over here is really about maybe a single character, right? It's about binary. If you think about it, so this is like a 0 or 1 over here. So whenever you want to say membership, 0 or 1 or any symbol. So these are individual symbol. Symbol here and also symbol over here. However, if you look at this particular, it's a string. It's not a symbol. Symbol is just a single character, right? You cannot say string is a member of a set of characters. It simply doesn't make sense. Okay. So this means if you say string is a member of a set of characters. Okay, this is what you're saying. And that one there simply doesn't make sense. You're not doing a compatible comparison. Okay? Yeah?
What about a symbol like \n for new line? Would that be considered?
Yeah, if you think there's a single symbol, yeah, that's kind of tricky the example here. I agree with you, yeah. But my point is, if you want to say set membership, you better be a single symbol. I think that's the main thing here. Yeah, good. Good. All right, let's move on. Okay, the length. When you talk about string, the length will just be, like a cardinality, really. Okay, so let's say you got a string over here. We got 1, 2, 3, 4, 5, 6, 6 characters. So length should be 6. That was easy. And the special string, which you maybe have seen before, is called epsilon. That one there is an empty string. Okay. So we got something called empty string. Empty string, we simply say epsilon. By the way, we don't really say this in this course, right? That one is kind of more programming. But epsilon here is more mathematical that we're going to use. Okay? Empty string, and then such that length of epsilon is simply 0. All right? That's why it's empty string. No character inside. All right, also concatenation. Yeah, so yeah, that's pretty easy, right? So if you say two string, x and y, if you want to concatenate them together, one followed by the other. That one's simple. And this part here is interesting. Okay? We say that the empty string is so-called identity for concatenation. So what does that mean? Identity. So identities. Okay, for this one, just for your knowledge, I'm going to summarize some interesting facts about identities. Okay, let's start with maybe string. Identities. So when you talk about string concatenation, okay, I'm going to do, this one here should be good. Let me expand that a little bit, okay. So when we talk about string concatenation, so first of all, let's have some operation. And then identity. And then we're going to supply some reason why. Okay, let's go over this. I think that should be good, maybe for today, right? Just when we're almost done with the string. If you talk about string concatenation, the identity is actually just empty string. Because if I get some string x, concatenate that with empty string will give me the same string. Also, doesn't matter if I put the epsilon here or here, right? In this case. Okay, that's the case for string concatenation. Identity is simply a value for which if you try to apply that value to some other operand for that particular operation, it will give you the same value back. But let's see, okay, just to test your understanding, okay? Very quick, okay? What about addition, numerical addition? Zero. That one's easy. Because a plus 0 equals a equals 0 plus a. And I'm pretty sure you know what's the identity for multiplication. Should be just 1, right? Multiplication. Would be just 1 because a times 1 will be a equals 1 times a. However, I do want to go a little bit further for you. Okay, let's talk about logic. What about conjunction? Logical conjunction. Oh, you know what conjunction looks like, right? Okay. What's the logical identity for conjunction?
True.
True? Okay, that's pretty good. You didn't guess, right? I'm pretty sure you know. Okay. If that's a guess, it's a good guess. Okay. True. Okay. Because P and true equivalent to P equivalent to true and P. Okay. And one more. And I'm pretty sure you know which one I'm going to talk about next. What about disjunction? And they should be symmetric. False. Because P or false equivalent to, P or false is simply going to be P. Yeah, exactly. Sorry. Equivalent to false or P. Okay, identities, right? It's a very universal concept over here. Okay. Okay, I think let's just see where we are. Okay, we're done with the first part of the string. And then I think for next time, yeah, I think this will be good time to pause. So for next time, we're going to pick up from here about just develop the string a little bit more, and we're going to talk about language and also problem, and then we'll go on to talk about regular expression. All right, thank you. See you next week.